Very efficient. Okay, joke aside, it's 15:20, so let's start and open the OPSEC working group session. It's chaired by 3 people for now, still for a few seconds, I guess. So let's start with Ron, which is the new co-chair, you know him. Günther, who is here and taking minutes today, is stepping down from the role of working group chair. So Günther, thank you for having my co-chair on this for a while. And my name, I'm Eric Vink. We have a JavaScript, which is Warren. And as I just said, Günther is kind enough to take the notes of this meeting. Please the note well. Everyone knows it, but we changed it recently. So in this IETF, the note well is slightly different than the other one. Basically, it says, whatever you say here is public. Blue sheets, you know the drill by now, filling your name and your affiliation. It's mainly to get a room bigger or smaller next time. That's important. Agenda. So we are doing this Administravia right now. We will spend some time mainly on one document, which is the OPSEC IPv6. I have striked out the AH filtering with the agreement with the other chair, because this document is basically ready for working group last call. We will issue the working group last call in the coming days. It has only 2 changes compared to the previous version. A lot of typos has been fixed, and the REPL options for the role of working group has changed numbers. It has only changed compared to the other one, so let's go there. Then I will present the OPSEC v6, the document which is there for many, many years. This is the only 2 working group documents that we have today. And as usual, we try to invite non-working group documents, because OPSEC is in the intersection of security and operation. So sometimes there are interesting documents in ops that are a security impact, and vice versa. Document in security that is an operational impact. So it's always interesting for authors to get the feedback from the OPSEC community here. And we will get Srinam, which has already presented a couple of times here, and maybe a working group adoption of this document. Then we have as well 3 with Nancy and Fleming. Jordi and Carsten will present their own draft there, mostly 15 minutes each. Administravia. So just said, we have 2 documents. I will present the OPSEC v6, and honestly, the AH filtering is ready, at least for me to go working group last call. We have only one individual document, which is the one that Sriram will present later this afternoon, and nothing else in the queue or whatever. Anybody want to change the agenda? Sorry. Okay, I take it for nobody want to change it. Let me know. That's always tricky, this stuff. Okay. So changing role. So Ron, you are the only one chairman now, but it's okay, I guess. So presenting this revision 13 of this document, and you will notice something has changed. We have 4. You know the story from Alexandre Dumas, right? The 3 Musketeers. It was Keke, Mary Kay, and Eric. We were always, all of us had got a K at least in our names, even 2 or 3 sometimes. So we needed somebody else, and we found an array. So just a few slides, one slide to introduce him. It's a well-known person out of Germany. I mean, some people know him here. He knows IPv6 very well and IPv6 security very well as well. He founded a company doing security, and is also running a conference called Troopers, which was last week in Germany, in Heidelberg. I was speaking there. A very nice conference. So, with this, and many other people that has reviewed the document, sometimes quickly, sometimes more profound. I see some of them in the room here, so thank you again. And just to give you a long history of this document, right? It started as an individual document in 2012, 6 years ago. And I had to put the history in 2 lines, basically. So a long time. It's also quite a long. So the change from 12 to 13 is mainly about 100 changes brought mainly by NRA. It's unable to come here today, by the way. Ron, you proposed 1 or 2. And Ule Tran proposed also many, as well as a few others. We fixed all the text using common sense, but there are 2 issues brought up by Ule and maybe others that I think we need to work as a working group there. Remember, the structure of these documents is the following. General consideration, which are basically what about IPv6? That's where we need to fix, I think, 2 points. Then something which is specific for enterprise, something specific for service provider, and something specific for home user. And if you look about the section about general security, you see a couple of points. And those 2 points are the one I want to talk with you today, or on the mailing list later. The addressing consideration needs to talk on ULA. When I talk to customers or other people, they always come to me, hey, Eric, what about ULA? So we need to have a section on ULA in this document. And of course, transition, we talk about tunnels. Even if we can say tunnels are a thing of the past, we still have IPv4 as a service over IPv6, right? So tunnels will stay here. So, don't kill me, right? But let's talk about ULA. And it is basically 4 paragraphs. And I hope it can Sander, can you read this on the back? Yes. Okay. So I put the text all there on one slide, just to get a change, right? If it's not correct. So ULA are intended for scenarios where IP addresses are not globally reachable despite formally having a global scope. Indeed, they are assumed to be unique. They must not appear in the routing system outside the administrative domain where they're considered valid. First statement with an security impact in blue. Therefore, packets with ULA source or destination address must be filtered at the domain boundary. I think this one is pretty obvious. Okay? I see nobody. Fred, you disagree?
I see. Well, since it can't be routed there, will the filter ever be activated?
So, is it never routed? To repeat your questions over there. Do the filter needs to be activated? As a paranoid guy, I say yes.
Well, so the question, you wanted me to repeat it, is that the firewall or the thing at the edge is not going to be injecting a route to the EULA into the domain. Mm-hmm. And so I don't know how the thing gets there.
I mean, routes, leaks, my answer, but Ron, you wanted to say something?
If I connect to your network, I'll just send you a packet. If you don't drop it, then you get the packet.
That's incoming. That's incoming. This filter is outbound.
Yeah, I mean, there is, of course, filtering on the source and destination. That's very easy to send packet with a source being in a ULA, obviously. And if your route leaks, you have an issue anyway. So I think it's better to filter source and destination. You do. That's the goal, right? I'm going to spend a few minutes on this.
I think, oh, no, we don't have.
Okay, anyway, the mailing list is still there, right?
Ron Bonica, Hatless. Shouldn't the filter be both on the source and the destination?
That's source and destination in the text.
Kind of the traditional problem with filtering source destinations was you could be breaking path MTU discovery.
But even if you break it, you can't have communication along that path anyway.
No. I mean,
No. Kind of the typical problem in path MTU discovery was that some intermediate hop was producing an ICMP.
You're right.
And
So only destination, you're right.
okay, maybe that's a pretty good point. I will change it only on the destination then.
well, okay, figure out whether it is actually a problem and how to if there is a need for a leak for that special purpose, how to define the filter so that only those specific cases are let through,
You mean
and not in general.
allowing source ICMP packets with packet too big, or this kind of parameter problem, or this kind of stuff?
If it is really a problem, I'm not completely sure.
Lorenzically, no, it has to be source or destination, because otherwise, if you forget to drop stuff with a ULA source inbound, I can send packets pretending to be inside your network, and I can bounce between two hosts on your network and send other hosts arbitrary packets, and they think they come from inside. And this is just like a bad idea. So it has to be source or destination.
Yeah. Well,
Okay. We can do it.
It's not a bad idea for the attacker. It's a bad idea for the network.
Ron Bunnick again. I agree, source or destination, but couldn't we have an exception for the ICMP PTB?
No.
Dear Ron Banica, here's a recipe for DDoSing a network.
Don't do that.
Exceptions are bad. So I think the point that's being
Jeff,
swirled
can you
around.
say your name?
I'm Jeff Hauser. I think the thing that's really being said here is that ICMP is the case that's causing a lot of grief. That probably should be dealt with separately, like find a global address to send.
Warren Kamari relaying from Fernando. Why not consider part of the bogons? Shrug. Okay.
Yeah. Anyway, so let's go. Oh, Lee.
Sorry, Lee Howard. This looks like the use of the passive voice, so it's not clear to me whether the filter should be applied inbound or outbound or both. I'd like that to be explicit.
That's a fair point as well.
Hi, Bob Hinden. I just walked into the middle of this. So is this different than what it says in 4193? Have you looked at 4193? Because it does have words about how you filter them.
Yeah. This document is basically summarizing a lot of other documents. So it should not contradict other documents, obviously, but can repeat what other document says. That's kind of a head start for security.
Well,
You're right, it does say it already on 193 section 4.
so quoting other documents is good. Summarizing tends to always lose stuff.
Fair point as well. Okay, so there's 4 paragraphs, right? So, so ULA assigned with pseudo-random /44 prefixes created as specified in 4193. They could be useful for infrastructure hiding as described by 4864, and we have at least 2 authors here of this network local protection. Tim and Günther, you were writing it. I put the sentence in red. Do we still want to get this sentence there? I mean, it's part of the RSC, right? So don't think it hurts. Perfect. Easy one. ULA may be used for internal communication in conjunction with globally reachable unicast address, UA, for hosts that also require external connectivity through a firewall. So meaning the host has got to UA to go outside and ULA on the inside. For this reason, no form of address translation is required in conjunction with ULAs when you use UA. I put it in green because I don't want to say translation here.
I know of multiple enterprise commercial deployments where there is no global internal addressing at all. They use ULAs and link locals exclusively, and they absolutely are natting at the edge. So
I would be curious to know.
so we need to, the wording right now appears to say that there is never a case where address translation exists, which is false. So maybe, hang on. So what the wording right now is not crisp and clear. And what I'm looking for is maybe some editing to make it more clear that there are some environments where it might happen, so that this is not viewed and read as a prescription against it.
And by the way, I would be curious to know the companies doing it, because I know about no customer doing ULA only in the inside.
So I regret that NDAs totally prevent that.
That's okay.
But they're commercial enterprise companies, and their security model that they chose by their policy is hard, crunchy exterior, soft, chewy interior.
Well, so Lorenzo Coliti, we I don't know how many years ago it was that this draft went to V6 Ops, and that text was torn apart. And the consensus on, I think, definitely in the room, and I think also even on the V6 Ops mailing list, was that we should instead say that this form of ULA only deployment is unspecified and not recommended. So I would argue that if we say anything here, we should say that this is not required and is also not recommended due to lots of problems.
Tim Chang, you could look at this comes up in so many places, and this draft is 7 years old, as Lorenzo said. So it's in the enterprise deployment RFC, it's in the ULA usage considerations draft that's been hanging around probably for about 7 years as well. And you just can't get consensus on it if you suggest or imply that running MPTV6 is a good thing.
Any comment on this one?
We should say it's not recommended.
Yeah, okay. You already said it, right? So you already said it, so it's mostly in the notes.
I'm fine with the language as it, sorry, Lee Howard. I'm fine with the language as it stands. I think that it doesn't imply that, that an alternative doesn't exist or is used. It's just saying it's not, the use of ULA does not imply the use of prefix translation. I think that's what it says. I think that's all it needs to say.
If it actually used your words, I'd be happy.
Oh, okay.
So the words being, that was Rand from the back saying if it used those words, he'd be happy. So the existence of ULA does not imply, does not necessarily imply the existence of prefix translation. It's in the record now.
So Arman, if you can capture this right sentence, I will be grateful for you.
Well, I don't agree with that sentence.
I'm just a JavaScript. Yeah.
Oh, no, so Gunther is taking the minute, so sorry. Okay. Anyway, we will not block the draft on this one, right? We should have a rough consensus, very rough in this case. And then the other one is basically saying, the last one, using ULA as described here might simplify the filtering rules needed at the domain boundary by allowing a regime in which only hosts that require external connectivity possess a globally reachable address. However, it does not remove the need for careful design of the filtering rules, obviously. Routers with ULA on the interface may also leak the address to the internet when generating ICMP messages or error messages ICMP that can also include ULA address as they contain a copy of the unfolding packet. So there's the other way that you were telling, basically. There's the inside here that is leaking in ICMP packet to big. So you will get, in any way, topology information in some case. Okay. So we are not fully agreement on this text, but I think we can maybe rewrite, basically checking here source or destination and doing something different here. Now, last point which is open to in this document is the text on tunnels. We still have text on tunnels that do not really exist anymore, like Teredo or 624. And Ule, chairman of Sixman, wants to remove the text on 624 and Teredo. On my side and on all the three other authors of this document, we do believe that people reading and starting to understand IPv6 security have those questions in mind. So we need to keep the text, even if it's kind of useful. And the text is pretty clear. It says that those two tunnel techniques are historic, but there is a chapter, basically. I think we got a consensus on this.
So apologies.
Tim Chan, does that apply to ISOTAP as well, which I noticed was in the document?
We only say Teredo and 624 are mostly historic and not used. ISATAP, we don't say this yet. But it's not really important, right? We are not about a designing network. We are about protecting the network. So that's basically as an author, and Mirike, which just joined the room as well. We want to go with the plus code on this one. Like last time when we try, we will send it to V6 Ops as well. So to get part of their comments. The audience is slightly different. And I guess as a chair and as the other chair, we can open the multi-group plus code next week. Lorenzo.
Comments on that?
Okay, comments are more than welcome.
I delay you even further, but since this draft was written so many years ago, the consensus in addressing best practices has changed. And so you have some text about disabling DHCPv6 and disabling privacy addresses, and
enabling DHCPv6 and disabling, I guess.
Sorry, disabling Slack and enabling DHCPv6 only. Needs to say that the best practice that this is not recommended, because it's a best practice that it's not recommended. 7934. Also, it says that IPv6 addresses are assigned based on MAC address using UI64. That's deprecated, not true anymore. Need to fix that. And yeah, I don't know.
Are you looking at the 13? Because the EU64, I'm pretty sure I fixed it.
No.
I was going to make the same comment.
That's right. Yeah, it's right here in front of me. And disabling privacy addresses is pretty silly, I think, for this purpose, because the document really needs to say something about layer 2 filtering and how you can't have layer 3 security without layer 2 filtering. And, you know, if you're not using Savvy, then it doesn't matter if you use DHCPv6, static, Slack. You have a hole that's wide enough to drive a truck through, and the document.
When we say Savvy, must be implemented, by the way.
Okay, but then you don't need this, right? So if you're doing Savvy, then you don't need to disable Slack, because Savvy can track this. This is all written, by the way. This is all written in 7934 section 9.1. So I guess what I guess I'm trying to say is section 2.1.4 needs an overhaul. 2.1.5, 2.1.6. Yeah, so that part needs an overhaul.
Okay, thank you for the additional job to do.
Yeah, Tim Chan, I was going to say some similar things. So yeah, 8064 is mentioned, and it just implies that you can use 7217, where in fact it's recommended that you should now, I believe. I don't think you cite 7934 at all, so you're not talking about multiple addresses. And the topic that I get from admins in my sphere is, gosh, with all these addresses, how do I account for the use of these addresses? So I think a section on address accountability, you do mention 802.1x, which might be there on Wi-Fi, it may be there on wired, but I think something a little bit more detailed about address accountability would be a good thing.
Okay. Thank you. Any other comments or suggestions? And they are welcome, by the way, right? Even if it means more work. But at least we will not finish with a 13, but maybe a 14. That's better, right? Better.
I think that if we were to send this to working group last call today, it wouldn't make it through. So a good thing to do might be to get a commitment from a few people to take a hard look at it. Maybe I can guilt Lorenzo into it. Lorenzo, do you have anything to feel guilty about? Okay, so you volunteered.
Thank you, Lorenzo.
Tim, you look.
Volunteer me, right?
What's that?
You don't want to volunteer me. You want a more friendly reviewer.
No. And
We can work with you.
Tim, you have a guilty smile on your face. So can I guilt you into it? So maybe we'll do a review in the next 2 weeks. Eric will update the document, and then we'll go to working group last call. And America.
Yep, Erica Cayo. Yeah, I was frantically taking notes. I came in a little late just so that I could capture everything that Lorenzo and everybody else was saying. To me, it's clear that whatever we say in ULA, there's going to be factions who are not going to be happy with it. So we're going to have to figure out what rough consensus is.
Yeah.
But I do think that at least the RFCs and the language and you know, what's been newer, right, from what we had created in the past, absolutely we need to make the changes of. So if some of you could just send even just the pointers to a paragraph, just say this paragraph from this RFC to the mailing list, right? Then at least Eric and I and maybe somebody, another author can capture that and we can, you know, that'll make it easier.
Okay, so we have consensus that Tim Lorenzo and whoever else cares to will review the document the next 2 weeks, send comments to the list, one more rev, and then we'll send that to working group last call. Tim?
Tim Chan, can you go back to the ULA slide with all the pretty colors on it? It's lovely. Sometimes saying less is better. So maybe that whole thing in green, if you just deleted it, you wouldn't have the controversy, maybe.
Yeah, I think that would probably work fine.
Well, we can remove completely this.
Well, no. You've still got,
We keep the paragraph, you just drop for this reason.
so you're basically saying if you want to communicate externally, you're kind of implying use GUAs alongside ULAs, and then you don't say, and therefore no form of address translation.
I think.
With you, right?
Yeah.
I was just trying to find something that might be mutually.
Now, if we remove the green sentence, that's the one which is having a vaguely security aspect. The first one has no security at all. So there's no point to be in an OPSEC document. Right? We are not making a design document. Okay, I guess for the sake of time, we need to switch to the next one.
These are your glasses, not mine. I won't be able to see a thing.
See that?
Fernando's also reviewing, offering to review. Okay.
Oh, Fernando wants to say a comment indeed. Fernando?
Yeah, it was just for presenting. I think that was needed.
Okay, thanks for the review.
Awesome.
My slides.
Oh. This is not your slide. Oops. I'm sorry about it.
So, good afternoon. My name is Sriram, and this is joint work with Doug Montgomery, who is here, and also Jeff Haas. So this is about enhanced feasible path filtering. I have, like Eric mentioned, I have talked about it a couple of times before and got a lot of good feedback. And based on that, we have been updating the draft. So quickly, the idea here is that strict URPF is not very effective. That is effective only in limited scenarios. Loose URPF is generally not very effective. And feasible path, what happens is that the way feasible path is currently defined, the ISP or the network provider is afraid that they may be denying legitimate traffic from their customers. So that does happen when there is multi-homing and asymmetric routing. So what we are trying to do here is to enhance the feasible path URPF. And the idea behind that is to try to see if we can encourage deployment with making feasible path URPF more attractive, more efficient in terms of how it works. Let's begin with like a definition, RPF list, reverse path filtered list. So this is the list of permissible prefixes for source address validation on ingress data packets on a given interface. So with that definition, this is the basic definition, I mean, the first definition, first algorithm for enhanced feasible path, we call it algorithm A. And for a good reason, later we'll also look at another algorithm that we call algorithm B. So this algorithm for the enhanced feasible path, so you look at all your customer interfaces and look at all the routes received on customer interfaces, make the list of unique list of origin ASs that appear in those routes, and then take one of those ASs and ask the question, for this as the origin AS, what are all the routes that I have on any of the edge ribbons? And you take that list of prefixes, and then whenever you see that you have the same origin AS on any of your customer prefixes, apply all the prefixes for that origin AS. If you received one prefix with a certain origin AS on a customer interface, then any other prefixes that you received on any of the other interfaces with the same origin AS, you apply them to that customer interface. It'll become easier if we go through some examples to try to grasp that. It's fairly simple. So this is a basic scenario where AS1 is a multi-homed customer. AS2 and AS3 are two transit providers. AS1 originates two subnets, P1, P2, and it announces only P1 towards AS2 and only P2 towards AS1. So in this case, what the problem that we are trying to solve is that there can be data packets from AS1 towards AS2 with source address in P2 and vice versa for AS3. So we want to be tolerant to that. And in order to be able to do that, we simply look at the customer interfaces and we figure out that we have two prefixes, P1, P2, both of which have a common origin AS1. So as long as that's the case, I would go ahead and apply P2 on the first interface on the left and P1 on the second interface on the right. So I'll apply P1 and P2 both. I'll include them in the RPF list. And by doing that, I'm offering the flexibility of accepting all data, source data packets from AS1 with the source address in P1 or P2. And and in this case, a feasible path doesn't work because they are not following the recommendation in BCP 84. That is to say that each of your prefixes, you should announce it to each of your transit provider. They're not doing that. In the next example, they are doing that. They are announcing each of their prefixes to each of their transit provider with prepending in order to depref certain routes. And in this case, feasible path also works. And all of these three loose, feasible path or enhanced, they all work fine. Now let's look at more interesting scenarios. Here we have the same, we have the S1 now having three subnets, P1, P2, P3. And P1 only goes along the left side route to AS2 and then to AS4. And P2 announcement goes in the middle route to AS3 to AS4, and P3 goes on the right side route to AS5 to AS4. AS5 and AS5 are peers, and AS2, AS3 are customers of AS4. So in this, again, AS4 applies the enhanced feasible path algorithm, and it figures out that I'm looking at this AS1, which is a common origin AS between these three prefixes. I look at P1, I got a prefix on this customer interface towards AS2 with a origin AS1. So now I would also add P2 and P3 to that interface because they have the same origin AS. So if the logic is that from an origin AS, if one prefix can find a path, the route can find a path towards me, potentially the other prefixes could also have come on the same path, and by extension, the data packets with source addresses in those prefixes could also have come on that same interface. So I generalize the URPF. So as a result, in this example, P1, P2, P3, all those three are applied on each of the two customer interfaces. That is the enhancement to the feasible path. And then Job pointed out this interesting, challenging scenario back in Prague. And here what is happening is that now AS1 puts no export. It announces P1, P2 both to AS2 as well as AS3, but it puts no export. So when from AS2, P1, P2 don't propagate to AS4, but they do propagate from AS3 to AS4. So again, so in this case, it doesn't work. Even the enhanced feasible path algorithm A doesn't work because it doesn't get any routes on the interface from AS2. So basically it is starved of routes, and it cannot apply that logic that is part of the enhanced feasible path. So we went back and thought about it, and then came up with an algorithm B. So depending on whether the operator decides that they have the less challenging scenario such as scenario 1, or the more challenging scenario such as scenario 2 here, they can, if they think, so if they have scenario 1 type of situation, they can apply algorithm A and it would be fine. And if it is scenario 2 that's likely to be applicable in their customer cone, they would use algorithm B. Algorithm B generalizes the algorithm A further. It makes it a bit more relaxed, and by doing that, it meets the challenge. So the idea here is that so this is the formal algorithm. Let me go to the example to try to explain how the algorithm works. So we have this scenario including the challenging part in which there is no export on the left side. So the way the algorithm works is that it looks at all the interfaces, customer interfaces. There are 2 in this case. And it makes a list of all the prefixes that were received on those interfaces, which in this case is P1, P2, P3. Let's call that the list P. And then it makes a list of all the origin ASs that were received on interfaces, on routes received on the customer interfaces. So in this case, there are 2 origin interfaces, AS1 and AS2. And then at that point, it looks for any other prefixes that were received or routes that were received from a peer or a provider, which might have one of those origin ASs. So by doing that, what it is trying to say is that I might not receive some of these prefixes on my customer interfaces, but with the same origin, I might receive that route from a peer or a provider. So I'm going to sort of relax and include those into my customer interfaces. So by doing this, it's taking the union of the P and the Q being the set of prefixes, unique prefixes that it saw coming from peers or providers, which happen to have origin AS that is in the set of ASs that are represented on its customer interfaces. And now it generously adds P and Q, makes the union of P and Q, and that's what it applies to all the customer interfaces. So in this case, it is able to meet the challenge, so to say, and P1, P2, P3, and P4, all of those are included in both customer interfaces, and as a result, it will not drop any of the data packets that may originate from AS1 with source address in P1 or P2, or from AS2 with source address in P3 or P4. Then Jeff Haas, who is the co-author.
You have 2 minutes.
Oh, thank you. So this says, so the question came up like, okay, what kind of requirement does it impose on the FIB? And we made some estimates of the worst case for different sized ISPs. And then we compare it with what kind of memory size is available. And as you can see, compared to this slide, the next slide, the available FIB memory size is order or 2 orders of magnitude larger. So that is pretty good. So it's not a significant increase in the FIB. So this is my final slide. So I wouldn't, all I said, like I said before, there are these 2 scenarios, the not so challenging and the challenging. And algorithm A works for the not so challenging, and algorithm B would work for the challenging type of scenario. Thank you. Questions?
Rüdiger Volk, Deutsche Telekom. First, on your first slide, I think your definition should clearly say that Yeah, that you are, oh yeah, okay, you did it. I just lost the word. Did you consider how the use of various anycast routing schemes actually interacts with what you are proposing?
Not yet.
Probably. Kind of that looks like it's going to have unintended consequences for the security. The other thing is kind of for the whole arguments are essentially arguing in a stable state of a routing system. Whenever you have changes, a failover, I would guess that the intermediate states will have packet losses.
Transient.
Yes, and in some cases that may be negligible. In other cases, it may be actually pretty bad.
Is that any different if you have, say, strict URPF or loose URPF?
Well, okay, with the strict kind of, you never would use that in cases where you depend on no packet losses. No, and so that's not really a relevant question, I think.
Loose maybe.
And kind of in general, looking at a couple of decades of evolvement of a routing system, I see that for something like 20 years, nobody cared about the transient states and the resulting packet losses. And well, okay, we got a little bit better, and for any new proposal, we actually should stay at that level.
Jeff, did you want to say something to respond? Okay.
So to answer Rudiger's specific point about, this does have situations where you didn't include, like your internal routing as an example or other stuff. This set of documents right now is not intended to be all complete at this point in time. This is more to solve here's what we see as a problem at the BGP level. If you think about the internal scheme of things, if you have some sort of internal routing, that information is also present and can contribute to this exact same list. So there are other possibilities to further seed things that are not directly up your same interface. This is a way of injecting additional information in. So that's a first thing. The second thing is, you're correct in terms of, do we really want to do this stuff real time? I'm going to tell you, we could not do this algorithm real time. It is big and messy, and there's a lot of state to do here. But in terms of, is it, from a functionally correct point, yes. So that's the goal that we're currently working towards, is functional correctness. Implementations will have to have hysteresis, memory. You want to eventually have it arrive at the correct filters that are good enough for a given period of time, and you're not going to try to update them super real time. And as long as you're not trying to do that real time behavior, you'll get most of the suppression that I think people want out of a BCP38 solution.
Igor Lubushev, Akamai. So obviously you guys are doing a great work in terms of you're in the right space. Security is very important, and BCP38 doesn't really work for complex systems. Just a few comments on the approach here. One is, so obviously algorithm 2 is not going to apply to big networks that have many customers, because essentially it becomes a no-op. It's also limited to cases where, so if you have a peer that basically did not receive announcement from another peer, that peer will still block you. Right. And the third comment about it is that, so you said that, well, if you want to deprioritize, just do a prepend, and it's a different AS system, it might not work. You might still get quite a bit of traffic that way. So one of the things we find is that if we want to be absolutely sure that we do not get traffic on a particular link, you do not advertise. And so that will cause more cases where it doesn't completely work. Last thing is that just want to say that I'm going to have a talk tomorrow in RTGWG on trying to solve basically this very similar problem, maybe in a slightly different way. So we should talk more.
Thank you. So just one comment regarding the large AS with large customer count versus small customer count. The focus should be on like not in the core ASs, but a little bit away from the core towards the edge. That's where it would. I mean, this kind of algorithms you would apply for URPF.
Right. Right. I mean, the biggest problem we find is that if we try to do something interesting in terms of traffic engineering, we could have a conversation with our partners, but then depending on how many upstreams and peers they have, they may be more reluctant to do any sort of allowances because it becomes harder for them to do it. So anything that will help in that area is thumbs up, and I mean, I really don't care about the particulars of implementation. So anything that in this area, I think is a very important area to work on.
Thank you.
Hi, Jared Mach, Akamai, recovering backbone operator, maybe. So one of my concerns, just about some of the data later on in the slides for, the fib scale and whatnot, is that often we're looking at, this slide, often when you're looking at service providers, many people are trying to shove their fib table inside of what are functionally switches, and based on the Broadcom chipsets, based on what they have available. When you're going and you're looking at this, a large, when you say a very large global ISP, anyone who really falls into that category has a customer cone that's greater than 128,000 prefixes. And that includes common folks like my former employer, Telia, and the list goes on. You go and you look at them, and somebody like Hurricane Electric, level 3 has close to 250,000 prefixes just in their customer cone. Mm-hmm. Trying to go and do an algorithm like this, I think, is going to be incredibly complex.
No, sorry if I didn't make it clear. We are not targeting the very large IS. That was just to say give the numbers, but it's
sure. But the one point I want to make is that if you're not targeting them, the issue here is the average AS path length has shortened significantly, as Rudiger mentioned, over the past 20 years, and the core tends to be more densely interconnected than it ever was. So we need to make sure that we're considering that use case when we're trying to do this. And the challenges in communicating between a service provider and all those customers about what prefixes are feasible and authorized to be announced start to sound very similar to some of the routing security discussions we have, where it is very difficult to signal that information to your upstream such that they can permit authorized prefixes, especially if you have disjoint islands or small regional networks or of some sorts where it's not always going to be consistent across the board, especially when you have limited lookup space in the hardware to actually do some of this. So those are my really big concerns that I have here. I really want to solve this problem as well as the routing security problem, but there's many parallels and corollaries here about just dealing with the scale and the scope of that.
Okay. Let me see. Jeff wants to respond first.
Yep, Jeff has. So thing number one, the actual implementation, specifically to Jared. Actual implementation, you're absolutely right. And the goal of this is not to say this can be done right now with current hardware. This is to say what a solution that is correct looks like. No, whether you can deploy it or not is a different question. Then after that, can you deploy it successfully in smaller things? The further you get away from SCID or core, the more likely you are to be able to get there. You're absolutely correct.
We start the discussion here, if you don't mind. It was 15 minutes allocated. We are already 25. Okay. I think it's a pretty dense discussion, so there's a reason why, and useful discussion, there's a reason why we let it go, but at some point of time we need to stop. Yes. I think it's a proof that it's an interest of the working group. So I think you were working, you wanted to get this document adopted as a working group document. So looks like it should, based on the discussion here. We will ask it on the, oh yeah, why not?
May I finish one last comment?
I finished, yes.
Our discussion with Igor came up with a very similar comment about other ways of injecting state. RPKI ROAS is another example of how you could get state into the system. So this does have nice intersection.
Okay, so let's have a hum. First, we will hum if you want to get this document or its next revision adopted as a working group document. So please hum now. Second hum, if you do not want this document in this stage being adopted as a working group document, please hum now. Slightly more in favor than in disfavor. Thank you. Next.
Just a quick comment. I didn't see during the presentation a comparison between the presentation about how to do, because yesterday there was a presentation during GROW about how to do feasible mode inside URPS. That seems very easy, and between and against your solution.
Okay, yeah, we can talk about it offline since I'm out of time. I'll be happy to talk to you.
So today I see two solutions for the same problem.
Thank you. Done.
Okay, thank you, Sam. So Nancy, it's up to you. By the way, anyone, the room is fully packed. There are a couple of seats in front. And I think we really need to get the blue sheet completed so we have a decent sized room next time. Anybody has not signed the blue sheet yet?
Can I go ahead and get started since we're running low on time? Yep. Okay. So thank you, Eric, and the chairs for inviting us to present this. So we have a draft that talks about the implications of the current set of network security solutions as we understand them, the implications of what will occur, what can occur, as we transition into TLS 1.3, and transition is the highlight here, okay? Okay. So basically, what do the network security solutions do today? They're there to provide auditing, monitoring functions, as well as access control and security controls. And so security controls fall into the area of beyond the access, and why we split them a little separately. The security controls goes towards not just compliance metrics, and some of you may already be aware of this, but to provide firewall all the way to intrusion detection, if you will, and intrusion prevention. So to generalize the solutions today, we'll look at the metadata, and I'll talk about it in the notion of how the traffic may be incoming or outcoming from a TLS perspective. So we refer to that as inbound versus outbound. And what these middle boxes, which we'll refer into some of the diagrams as TLS proxies, do. And so even in there, I show some diagrams into which these middle boxes are basically being passive. They're just trying to observe passively, or they're being proactive, and I'll describe what we mean by proactive there. So redundantly, you'll see in some of our diagrams, we refer to them as middle boxes, but in the actual flow diagrams, we call them out as TLS proxies. Proxies from the notion of, especially when they're being active, if you will. In that sense, they'll act as a proxy, meaning from the TLS client, the proxy will act as the TLS server, and then to the actual TLS server, the proxy will act as the TLS client, okay? Okay, so one of the scenarios that we talk about is what we refer to as the outbound scenario. meaning that from an administrative domain, the client is inside your administrative domain trying to talk outside. So web applications, for example. So in that instance, what the proxies will do in a proactive scenario, if you will, is they will provision the client, the TLS client, with the local or the TLS proxies root cert so that the TLS client can actually authenticate and validate the proxy. And then obviously the middle box will have its own local certificate that will either be cached or can be provisioned at the time that it needs to actually act as the proxy. So all of this, when the proxy actually takes and comes in, is only when the policy gets lit up and says, okay, I actually need to come in and act as a proxy. Okay. Similarly on the inbound. So again, in these scenarios, this is all based by the policy enforcement, and so it's only at the time that it needs to enforce. So again, in this scenario, in the previous one, it was the client being inside the administrative domain. In this case, it's the reverse, where the client is trying to come in to your administrative domain. And so in this case, the proxy is leveraging the TLS server cert. So in some cases, especially how we're leveraging the static RSA keys, is so that it can come in and inject himself in the middle. Okay, so I'm not going to, in the interest of time, call out each and every one of the use cases, but they are enumerated and there's more description in the actual draft. But as you can see from the outbound case, we've tried to enumerate them, and if I were to just do the general categorization, a lot of them go towards, again, policy decisions, whether it's for access control or from a security perspective, especially down as we get to looking at posture and compliance. So let me just leave it as that. So I want to also call out my co-author, Fleming, is here, who will help me field Q&A, and I'm looking at him to make sure I haven't missed anything important as I'm trying to rush through this. Okay, so for the inbound, those use cases, again, they're very, from a general category, they're very similar from the standpoint of what we're trying to do is protect the data resources in your administrative domain, which is why we've called out some of the use cases there. The other one that we've been hearing requests for, which we've listed in the bottom, and again, this gets to the auditing and compliance, and that is from a cryptographic perspective on doing the crypto security audit. Okay, so now what I'm going to walk you through very quickly is just what happens today with the current TLS 1.0 to 1.2, where the middle boxes or the TLS proxies are either being passed through or actually being active, if you will. So in the pass-through, in a very general way, basically the middle box is inspecting and gleaning as much information as it can while the TLS session is being established. So today, up to TLS 1.2, most of the information, the identities, the negotiation of the versions, as well as the cipher suites, do come in clear text. They're not encrypted yet. And so from there, the policies can make the early decision before that tunnel is actually established, whether and how that access control may get affected, okay? In the actual proxy, or what I'm calling an active state, The middle box is really acting as that proxy, meaning as the TLS server to the client or as the client to the TLS server. And so in here, it can still do the inspection because the information is in a clear text, but now what it's going to do is it's actually going to get an active or have the ability to encrypt and decrypt the application data, if you will, so that it can further do deeper inspection of the data for doing things like application level intrusion detection, as an example. Okay, so now let me go through what happens and to summarize some of the impacts, and I apologize for some of the typos here since we were working on this rather late. So with TLS 1.3 today, and I haven't inserted the middle box here yet, what happens today is that in the client hello, we're now enforcing the use of ephemeral Diffie-Hellman. There's no more static RSA keys for authentication. In essence, what we do with TLS 1.3 is split the actual tunnel session from the authentication. Yes.
Hi, Stephen Powell. Just a point of information. Diffie-Hellman is supported in early versions of TLS.
Understood.
That's not a difference in 1.3.
I'm not noting that as a difference. What
Your
I said,
draft does.
I believe what we state is it is now enforced. You must always use ephemeral Diffie-Hellman in the initial tunnel establishment. Okay? So basically, there is a draft there that is proposing that we obscure even in the client hello the server identification, which can become an issue. The other ones that I'll call out is in TLS 1.3, they've optimized the number of handshakes. They achieve this by effectively compressing in the server hello and all of the other messages. They begin to encrypt the messaging there, including the information of the server certificate, basically. So effectively, what this means is that in that handshake, we can no longer inspect the cipher suite that resulted in the negotiation, as well as the identity of the server.
You have 3 minutes left.
So I got to talk faster, which will be challenging. Okay, so I'll go faster. So now inserting the middle box, basically what this means is we're now restricted as to what we can do and what we can achieve, both in the access controls and the security controls, especially the notion of now in the optimization of doing resumption with a 0 round trip. They're now using pre-shared keys, but this now may become prohibitive if we can't get the full information. So I'm going as fast as I can. So I'm not going to list out the impact here. It's in the draft. The summary here, basically, I think I've already stated, because of the obscurities, especially during the handshakes, it will be much harder for us to make decisions on the initial access control, even on the resumption, as well as the security controls leading up to the intrusion detection capabilities. So this is the example for the outbound. And again, highlighting the one that I wanted to call out, the encrypted is a separate draft right now that hasn't been adopted, but we wanted to highlight here. I didn't think it was Christian's draft. Okay, my co-author just corrected me that that draft is adopted. So, okay. And so similarly for the inbound use cases, especially for doing the crypto security audit, it'll be much harder for us to do because we can't see what the final cipher, negotiated cipher is. So basically we are working.
Kenny Patterson.
Yes.
In TLS 1.3, there are precisely 2 ciphers that are currently standardized. AES GCM and Cha-Cha Poly 1305. Which one of them do you not like? that you want
It's
to know
not that I
about?
do not like them.
Sorry,
It's
which
whatever.
one? Which one do people want to distinguish between?
It's not up to us. It's up to our customers to determine what they want to enforce using.
I guess your customers need to
Or-
come here and make this presentation then, because that's, to me, that sounds like a non-requirement unless they're here to speak for their requirements.
Oh.
Well, hang on a second. So the cipher actually is indicated in the clear in the handshake. So
The resulting one, I thought it was encrypted.
I assure you it is in the clear.
And Eric, state your name.
Eric Riscola, TLS, one with your draft editor and one of the main implementers of NSS. I assure you it's in the clear. It's got in the clear because that's how you do that. It's in the clear because otherwise you can't decrypt the handshake messages that follow it.
Okay, your point is well taken.
Nancy Elkins. Thank you very much for doing this, Nancy. We would like to have a solution as well to a number of the issues posed with TLS 1.3.
Hi, Stephen Farrell. Is it time for Q&A?
Yeah, very short. And Q&A, no discussion too much, right?
Okay, my name is Stephen Farrell. This draft is riddled with inaccuracies. There's many places where it makes assertions that things are impossible, which are just not true. There are ways around things. So, for example, you claim that you can no longer kind of see if somebody's using out-of-date certificates. You can easily survey servers in the network, et cetera, et cetera. There's a longish list of inaccuracies here. But also, I'm kind of curious as to what the point of this draft is. Given that TLS has discussed some of these issues, what is the point of you producing this draft?
So it was requested that we put out how network security solutions are behaving today. So all I'm trying to do is articulate the behavior of security solutions today. I'm not saying TLS 1.3 is bad. All I'm trying to state here is it's actually good. Well, anyway, you're quoting that I have inaccuracies in the draft. We've discussed some of those. I don't see how they're inaccurate because I tried to quote some of the regulations. So we can debate that. But anyway, my point is I did this because it was requested. All we're trying to show is there's going to be a transition period, okay, in the notion of how, as network security solutions evolve, we now have to account for how do we deal with the fact that we're going to have clients that can only support 1.2. I'm not sure if clients moving forward. In the IoT case, those clients are going to take a long time if they get upgraded at all to TLS 1.3. Okay.
So again, I think it would be interesting to describe the network security things people do. I think the idea of kind of at the end of each section of trying to do that, say, here's why TLS 1.3 is bad, which is how I read what you've written, is not a good idea. I don't think the existence of a draft like that is useful.
So Fleming isn't co-author on the draft. So Stephen, first of all, it would be very helpful if you were to, suggest some text clarifications to the draft. We would welcome them from anybody, right? The goal of the draft is to try to understand what are the implications of TLS 1.3 to network-based security solutions. That's what we try to highlight. If there are inaccuracies in there, let's get them corrected. If you're saying all of these issues that we call out, they are solvable, by all means, let's document how we solve them. That is the purpose of this draft, and we welcome any help we can get, but we haven't gotten help yet.
Okay, let's finish very quickly. Lee, very short, please.
Lee Howard. I haven't done a full comparison between the two documents, but I think there's some overlap with draft MMWG effect encrypt, which right. So, and I think and I didn't see a reference to that draft at all. And I think that since there is some overlap, there at least ought to be a reference.
Okay, thank you. Very quickly.
Yeah, Martin Thompson. There are inaccuracies in this, and your presentation actually shows a key synchronization attack that we've actively worked against in TLS 1.3, and that particular usage is highly unsafe in various contexts. And I'm kind of surprised to see that people providing these sorts of network security services would actually deploy that sort of thing, because it completely compromises security with certain cipher suites. So that's a real concern. So The meta point, though, is why is this not in TLS? Why are we not having this presentation in TLS?
So,
Because this is directly relevant to that group.
yes, and when I approached the chairs, they said we had not had enough discussion to warrant getting a slot there.
Okay, let's close now. We have still two papers to go through. And thank you, Nancy and Fleming. Jody, it's up to you. You have 10 minutes rather than 15. We can still push the discussion at the end, but please try to do it.
Try to go faster. So, hi, I'm Jordi from UPC Barcelona Tech. Well, first of all, I would like to thank the chairs for inviting me to present our draft. We're always happy to share our ideas. So, how many people here know about Bitcoin? Okay, let's go. So, first of all, I will make a short introduction to blockchain and Bitcoin for those who are not familiar with it. Then I will explain how it would be useful to store IP addresses. I will try to discuss some considerations regarding operational considerations. I will end up with some data on our prototype. So first of all, blockchain. Blockchain, very short, is a decentralized, secure, and trustless database. So you can see it as a token tracking system. So a way to know who has what. It's built adding blocks of data one after another. And it's protected by two mechanisms, a chain of signatures, which ensures the ownership of the data tokens, and a consensus algorithm, which ensures the integrity of the data. So as you know, the first blockchain ever built was Bitcoin. It can be used to exchange money between two parties. You don't need any intermediary, but other applications are possible. So in this slide, we summarize briefly how blockchain works. So the basic unit of a blockchain are transactions. A transaction has three elements, data, the sender's signature, and the public key associated with it. So when you want to add a new transaction, you broadcast it to a peer-to-peer network. At some regular intervals in time, a designed node collects all these transactions, adds them into a block, calculates the consensus algorithm, and sends the block back to the network. All the nodes in the network receive this block, they verify the transactions and the consensus algorithm, and if they are okay, they add the new block to the chain. Since the blocks are linked one after another with their hash, that's why it's called a blockchain. So this slide presents a summary of the features of a blockchain compared to traditional PKI systems. So the advantages is that it is decentralized, so there is no hierarchy. You don't need certification authorities, which makes management more simple. Rekeying is also very simple. You need a limited prior trust. It's auditable because you have a history of all the transactions, and it's censorship resistant because added data cannot be modified. And of course, it has also some drawbacks. The first one being that you don't have crypto guarantees like in a PKI. It rather depends on the good behavior of its participants. It also requires larger storage because the blockchain keeps always growing, which also makes bootstrapping costly because you have to download all the blockchain. So how would this work for IP addresses? So basically, you want to store three things in the blockchain. Who holds an IP address and its public key, the chain of allocations and delegations of IP addresses, and the binding of these prefixes to AES numbers. So why blockchain? It's a must-do question. We can see IP addresses as coins. They are not exactly equal, but they share some similar properties. So they are unique. Two people cannot have the same IP address. They are transferable. I can send addresses to someone else. And they are divisible because I can split a prefix of IP addresses and allocate each chunk to a different entity. So we can see this idea as a means of sending IP addresses to other people, like in Bitcoin, you send money to other people. So quick example. So this blockchain would start with Ayana. Ayana writes a Genesis block, which is the first one, saying I have all the prefixes. Then it starts allocating prefixes to the registries. And then the registries allocate prefixes to its customers, like, for example, an ISP. And finally, an ISP adds a transaction binding its prefix to its AS number. So then if I want to know which is the AS number associated with a prefix, I just have to read the blockchain, get the last transaction associated with this prefix, and I know the AS number. And I can always go back to the history of transactions to check if this prefix was originally owned by IANA, thus making sure that it does not come from a legitimate source. So I don't know how I'm running in time.
You have 5 minutes.
5 minutes, okay, perfect. So operational considerations. So in Bitcoin, there is no revocation. So that means if you lose your keys, you lose your money. It has already happened. But we believe that in our scenario, if you want to store IP addresses, this does not make sense because IP addresses they are finite, they are a public good, so they cannot be lost. And also, you have some other cases if the keys are compromised or if there is some improper use on this prefix of addresses, for example, that the customer does not pay the registry's fee. So basically, we are between two scenarios. In a traditional PKI, there is a centralized control, and in Bitcoin, it's totally decentralized. But in our use case, we think that the best situation would be a middle ground. So in other words, I don't want any upstream registry revocating my prefixes arbitrarily at any time, but I want to leave the door open because at some point in time, I may have a problem and I want to fix it. And to solve this, there are some possible alternatives. So for example, you can add a timeout to a transaction so that after, for example, 1 year, this transaction expires and the prefix automatically goes back to the previous owner or the registry. There is also multi-signatures which allow you to secure a transaction with several signatures. For example, you could leave some room for the registry to revoke the transaction and then recover it, or also add a special type of transaction that revokes the prefix, but only issued by a third party, so that it's external from the two disputing parties. Well, now rekeying, that's the simple one. Rekeying a blockchain is very easy because you just have to delegate your block of addresses to a new keeper that you control. This can be performed individually, and you don't affect other holders. And finally, a few words about privacy. So a blockchain is a public ledger, anyone can access it. So we must restrict which information do we write in it. So our vision is that in the blockchain, you should only have the pairs of prefixes and public keys, and any private data like business relationships, internal registry policies should be kept private, and changes in these policies should only be reflected by an update on the prefix and public key pairs. So finally, we built a prototype to test our idea. It's written in Python. We use a simple proof of stake. There's a block time of 60 seconds. We use 2 megabyte blocks, and we support both IP version 4 and IP version 6. And we have open source it here, so you can have a look if you want. And we carried out the following experiment. So we have a master node that has a Genesis block with all the IP address space. And first, it allocates all the /10s to 8 nodes in the system. Then these 8 nodes allocate between themselves all the /16 addresses. And finally, these nodes allocate again between themselves around 130,000 prefixes that we extracted from the registry's exchange files. And well, how did it go? So here you have our test run that lasted more or less 24 hours. You can see the block number and the transactions that every block had for version 4 transactions and version 6 transactions. And here you can see in this small space the first allocation from the master to the 8 nodes. It was more or less 50 blocks. Then you can see here around 300 transactions per block, the allocation of the /16s. It is very regular because all the nodes have the same number of transactions to do. And then finally, you can see how we allocated all the registry files prefixes. It's more irregular because the delegations tree is unbalanced. So With this, I mean that
You need to say to finish now.
it's the last one. So I mean that the delegation tree is unbalanced, and some prefixes have a lot of subprefixes, and others don't have so much. So nodes run out of transactions at different points in time. So just to note, the chain was around 1.1 gigabytes for these 150,000 prefixes, and it took more or less 6 hours and a half to bootstrap it. Thank you.
Due to the time constraints, I will not allow any question or answer. So Carsten, next one. The last one. So after this, you can go to the questions to Jordi, because I think it's an interesting topic.
Yeah, I'm happy to discuss it offline.
So I'll just start. Well, do you have a clicker?
Yeah.
Okay. Yeah, so my name is Carsten Rosenheffel. I'm with ENTC, Independent Test Lab in Berlin, Germany. And we've been testing firewall performance, network security solution performance for many years. And more recently, it started annoying us a lot that what we find in our tests is very different from what we find in data sheets of vendors. And I'm not sure if you've seen that. There's always been a discrepancy, but it's getting worse and worse, especially with like next-gen firewall functions, intrusion detection, unified threat management, all of these more advanced functions. And so we got together with a group of like 6 vendors who actually started to see like their data sheet numbers are starting to hurt them because their customers don't trust them anymore. And two test tool vendors and 3 test labs. And we started to create a new next-gen firewall benchmarking methodology. That was actually initially outside IETF, and then we looked for a home that's for our standard that's has a good reputation and is looked at both by enterprises and service providers. So that's how we came here. The point is actually to create a benchmarking methodology for next-gen firewalls, IDS, UTM, web application firewalls, and a couple of enterprise and service provider use cases, and especially to strongly improve the reproducibility and transparency of benchmarks. So we want to take this document, which we're currently developing in the benchmarking methodology working group, we want to take this as the basis for an open multi-lab, multi-tool certification program. So there are a couple of use cases. We are starting with the enterprise perimeter firewall, but subsequently we'll add profile data to the draft to cover a number of the other scenarios. Maybe some of them have to be postponed depending on the workload or depending on the number of contributions that we get. And in general, we focus on the performance benchmarking methodology, especially heavily looking at encrypted communications performance, of course, but also the security effectiveness tests. Because if we look at today's market for security effectiveness testing, it's mostly opaque. So individual labs have like mostly, undisclosed or semi-disclosed only via paywall, disclosed security effectiveness tests, which doesn't help the industry to improve. So we want to make the attack vectors public and standardize them. Of course, there is a lot of dynamic in attack vectors, so we can't just nail them down in an RFC and keep them fixed forever. So we will have to refer to external databases that are public, such as the NIST database, for example. So I think I don't want to run through each of the slides. Please, if you're more interested in more details, look at the slide deck that's part of the materials. Generally, we're looking for contributions, of course, and for review, and in general for interest in the initial coverage areas that are shown here on the slide. So obviously, there are a lot of functions beyond just basic forwarding and rule-based filtering that the next-gen firewall has to implement. And some of them require effectiveness tests. A lot of them require performance tests. And in most cases, they actually require a security effectiveness, like attack tests, together with a performance background. Because most of the tests are done in lab environments that are not very realistic these days. So either you test functional attacks, it's like the firewall sits there, it's completely idle, it just waits for something, and you send it one attack, it handles it nicely, you say like, wonderful, this firewall does well, but you have no idea how this attack actually influences the performance of background load. So it's actually about much about making tests more realistic. I think the combined experience of the 3 labs that are involved and all of the vendors will enable us to provide a much better standard than in the past. So there is an old document called RC 3511, which exists for 10 years, was also created from the benchmarking methodology working group for old legacy firewall tests. I think our document is going to supersede it, but of course 3511 will still be applicable for like lab-based testing of traditional firewalls. So I think I can skip most of that. One last thing, maybe traffic mix. Actually, firewalls are usually tested with a very uniform traffic, like let's use as large as possible request sizes, let's use as few as possible certificates, and so on. And this helps the vendors to typically optimize the memory in their firewalls so that the data sheet numbers are blown up, or grown if you're a vendor, increased. So, and the traffic mix that we'll define in an annex will actually help to make this testing more realistic and will prevent this kind of optimization that is not real. So we have a pretty aggressive schedule. There are quite a few contributors. We hope to get this through until August. Oh, a couple of questions. That's basically it. And based on this IRC, once it might have been ratified, approved, we want to create a certification program. Please.
So, if you just go back to sorry, this is May Selnadai from University of Essex. Yes, are you actually going to define traffic mixes based on services, not actually protocols or application layer protocols? Are you actually going to do Google Maps, Cisco WebEx, etc., etc.?
So the important part here is it's all web-based traffic. So for an enterprise perimeter, probably that's realistic. So the important part here is to have unique certificates, and the certificates are supposed to be real, because that's, and apart from that, I don't care whether it's Outlook or YouTube or whatever. What counts is the number of URLs, the number of domain names, and so on.
Yes, well, I come from a slightly different angle, and my interest is actually, often you look at traffic mixes and they are TCP, HTTP, and you don't know what's the mix inside actually. But security threats, particularly in next gen, is more about the services that comes with the organization. So I'm quite interested, is that going to have a follow-up with some traces or some data acquisition or some analysis that shows certain profiles?
Yes, and this is only the first profile, so if you're interested in contributing something, that would be more than welcome. Currently, this profile is implemented in one emulator. Another from Spirent, another company, Ixia, or Keysight, is about to implement it, and we also want to make it available publicly as a capture, like a PCAP that can be played by a open source generator such as T-Rex.
Great, I'll follow up in details later.
Okay.
Then. Thank you.
Tim Chang, so first of all, maybe a very naive question. What's NetSec Open? You don't link to it in the draft.
No,
you mentioned it 5 times.
I did, sorry. So it's a non-profit organization, a 501c US non-profit, and like any other industry association, we need a body to host the certification program.
Okay, so my comment on the testing, I don't see anything there about doing really high throughput flows in the mix with all the other daily cruft that, for example, a university campus would get. So something that's really big in universities at the moment is being able to push several gigabits a second of flows through the firewall while all the other stuff goes on. Most universities now are starting to engineer the network, so the high performance stuff is redirected a different path into the network, but having some measurements of existing firewalls to show just how bad their architecture is at mixing those two types of traffic would be really useful, but I don't see that in there at the moment.
Yeah, that's a great comment. I think we started with a normal office environment, but obviously we have to look at like how many profiles do we actually need to have a realistic test.
That's a growing one in university circles.
Okay, good, thanks.
Jeff has a question and a comment. The question is, would IKE be one of the things that's worth testing as part of these profiles?
Well, yes. I think we have an ongoing discussion about which ciphers and which which encryption options we should use. I'm not the best possible expert on the details, but we have actually weekly calls, so I'm happy to invite you.
I'm not appropriate. I'm inappropriate to invite. It's not my field. The second question, well, second observation is about your traffic mixes. One of the things I strongly recommend is that you have traffic mixes that not only are large full frames that you're doing at the appropriate throughput rate, but lots of small frames that are high packet per second. What is a generally known thing in forwarding hardware is that high PPS can be more damaging than high BPS.
Right, of course. Thank you.
Al Morton, co-chair of the benchmarking methodology working group, where we would really love to see all these interested parties, and I know who you are, show up and make comments so that this draft will get adopted, and we'll incorporate it in our work plan. Thank you.
Yes, thanks very much.
Okay. Some last word, maybe? Okay, finish. Okay, thank you so much for coming here. Jody is still in the room, I guess, if you have any questions regarding the blockchain. If you have not signed the blue sheet, that's mostly now or never. And see you next time in Montreal, or Montreal, as you say.
Too many questions and nothing, right? Will they turn the clipboard or just the? No, we need to be there.